Hello everyone, and welcome to this session of solving the problems. In this session, we will solve the problems on laws of motion. So let's start with our first problem. Our first problem is a block of mass 2 kg placed on a long frictionless horizontal table is pulled horizontally by a constant force F. It is found to move 10 meters in the first 2 seconds. Then find the magnitude of the applied force. Let's solve this. First, see what are the different values of the parameters provided here. We are provided with mass m, which is equal to 2 kg. Distance traveled by the body s is 10 meter. Initial velocity u was 0 because the body was at rest. And time taken in traveling this distance 10 meter was 2 seconds. So these values are provided and we have to calculate the magnitude of the force that was applied on the body. For this, let's start with this equation, which is which tells us about the distance in terms of velocity, time, and acceleration. That is, s is equal to ut plus half at square. We know that initial velocity of the body was 0. So this first term here will be 0. And we are left with the second term only. So the displacement can be written like a half at square. And here, putting the values of s and t, we can calculate the acceleration. We already know the value of s, that is 10 meter, and t is 2 seconds. So the value of acceleration comes out to be 5 meter per second square. Now we know the acceleration and we already know the mass of the body. So we can calculate using this formula, A is equal to F by M or F is equal to ma. This is the second law of Newton. From here, putting the values of mass and acceleration in this relation, we can calculate the force that comes out to be 10 Newton. So 10 Newton is the force that was applied on the body to drag it by 10 meter in 2 seconds. So this is our answer of this problem. Now let's move to the second question. Our second problem is a ship of mass 2 into 10 to the power 7 kg initially at rest is pulled by a force of 7 into 10 to the power 5 Newton through a distance of 3 meter. Assuming that the resistance due to water is negligible, calculate the speed of the ship. For solving this problem, first see what are the values that are provided here in this problem. And we see that mass is provided m, that is equal to 2 into 10 to the power 7 kg. Force is provided F, that is 7 into 10 to the power 5 Newton. Initially, the ship was at rest, so initial velocity u will be equal to 0. Distance traveled s is 3 meter, and we have to calculate the final velocity. For calculating the final velocity, we can use this formula, which is v is equal to u plus at. U is the initial velocity, a is the acceleration, and t is the time taken. We know that initial velocity u is 0, so we can write v is equal to at. Here, acceleration, the value of acceleration is not provided. The value of time is also not provided. So we have to convert these things, or we have to rewrite these parameters in terms of the values that are provided in the problem. For this, we can write A in terms of force and mass using this relation. This is second laws of Newton. And if we write acceleration in this form, then we can write velocity is equal to force by mass into time. Again, we have to write this time in terms of the known parameters. And for this, we can use this relation, that is s or displacement equal to ut plus half at square. Here, because the initial velocity was 0. So this term is again 0, and we are left with the s is equal to half at square. So from here, we can write the time in terms of displacement and acceleration. And if we further write this acceleration in terms of force and mass, that are the known parameters, and we put this value of t in the relation of v is equal to at that we have discussed before in previous equation, then we can write the final velocity in this form, that is square root 2 times displacement times force divided by mass. Putting the values of all these three parameters, s, f, and m, we can calculate the velocity from this relation, and it comes out to be 0.45 meter per second. So this is the final answer. This is the final velocity that was attained by the ship when it was dragged by a distance s and by the given force that was applied on the ship. Now let's move to the another problem. Our next problem is a block of mass m slides along a floor while a force of magnitude F is applied to it at an angle as shown in the figure. The coefficient of kinetic friction is mu. Then what will be the value of acceleration of the block? So first, let's understand this problem using this diagram. So this is the body of mass m, and it is sitting on this surface where the coefficient of kinetic friction between the body and the surface is mu. We are applying here a force F on the body at an angle theta with this plane. To solve this type of problem, first let's understand all the different type of forces that are acting on this body from different directions. So here we can see we are applying the force at this angle theta with respect to this plane. So we can split it into two components. One is along this surface, that will be F cos theta, and one is perpendicular to the surface, that is F sin theta. On the body, there will be another force perpendicular to this surface, that will be the reaction force defined here as N, and another force that will act downward, that is because of the weight, that is mg, and one force because we are saying the body will move. So one force will be the frictional force that will be in this side, that is opposite to the component of this force, and that is defined here as small f. Now let's see what will be the values of these different forces and how they will relate with each other. So N here, because there are two forces acting on the upper side perpendicular to the surface, and one force is acting on the downward side. So if we take these forces, then from these three forces we can say for the equilibrium state, because the body is not moving in this direction or in the downward direction, so N will be equal to mg minus F sin theta. And for moving the body in this direction, because we are applying the force along this direction, and we are applying the force F cos theta. This is the component of the force that is acting along this direction. So if it is moving, then it must be F cos theta minus F equals to m times the acceleration. F is the frictional force. The value of frictional force can be calculated using mu, that is the coefficient of friction, times reaction force, that is N. Value of N is already defined here in the relation 1, which comes out to be mg minus F sin theta. And taking this value of F and putting it in this equation 2, we can calculate the value of M A as F cos theta minus mu mg minus F sin theta. From here, we can write it in other way, like A is equal to F upon M cos theta minus mu times G minus F by M sin theta. In this problem, the values of force, mass, or theta were not provided. So we can write acceleration in this form, and this is our final answer. Our next problem is a block of mass 4 kg rests on a rough inclined plane, making an angle of 30 degrees with the horizontal. The coefficient of static friction between the block and the plane is 0.7. Then calculate the frictional force acting on the block. So let's understand this again using the block diagram. So here, this is our inclined plane. This is the 30 degree. Here is our body, whose mass is given as the 4 kg. So this will be the component of the force because of the gravity and mass. This will be equal to mg here. And this will be the reaction force because it's resting on this surface. So it will be normal to this surface. And we can see that this force, we can split into two components. One is perpendicular to this surface on which the body is resting. That will be mg cos theta, because this angle will be equal to this angle. This relation we can find using the simple trigonometry. And another component of this force, mg, will be along this plane. That will be mg sin theta. So this component, that is mg sin theta, may result in moving of this or sliding of this block in this direction, that is downward direction. But there is another force acting on the opposite direction, that is the frictional force. So as given in the problem, this body is at rest, it's not moving down. So in that case, there must be a equilibrium, and under the equilibrium, we can define it as the force, that is the frictional force, that is acting on the upward direction must be equal to the force that is acting on the downward direction. So if we put the value of m, g, and theta here in this relation, then we can, using this simple relation, we can calculate the value of this frictional force that is acting on the upward direction will be 4 into 9.8, that is the value of g, into half, that is the value of sine 30 degree. And the final answer will be 19.6 Newton. This is the value of the frictional force acting on the upward direction, so that particle will stay at rest on the inclined surface. After this, let's move to the another problem. Our next problem is the pulleys and strings shown in the figure are smooth and of negligible mass. For the system to remain in equilibrium, what should be the value of angle theta? So let's understand this problem. Here we have two masses of mass m each. One is here and another one is here. And the third mass our next problem is the pulleys and strings shown in the figure are smooth and of negligible mass. For the system to remain in equilibrium, what should be the value of angle theta? So let's first understand this problem. We have three bodies. One here that is of mass m. Another one is here that is of also the same value of mass, that is m. and third body is here, that is of mass square root 2 m. They all are tied with the strings of Our next problem is the pulleys and strings shown in the figure are smooth and of negligible mass. They are shown here in this figure. For the system to remain in equilibrium, what should be the value of angle theta? So let's understand first this problem, which is shown here in terms of these block diagrams. That we have here three bodies. One is here, that is of mass m. Another one is here, that is of mass m. And third body is here, that has the mass square root 2 m. These all three bodies are tied with two strings. They are inextensible strings, and the pulleys are frictionless or smooth. Here, this is the angle with respect to this plane. This angle is theta, and considering that this whole system is in equilibrium state, we have to find the value of this angle theta. So as similar to what we did in the previous problems or the questions, here again, first we will identify all the forces and their directions acting on all these three bodies. And after knowing the forces, we will solve our problem. So here we can see different forces acting on these bodies. First, we can see this is the tension here, tension in the string, because this body is tied with this string, and this is an equilibrium. So this tension in the string will be equal to the mass into gravity, that is the force due to gravity here on this body. So we can say this T1 will be equal to mg. This body also has the same mass, so tension in this string will T2 will also be equal to mg. Now let's see the third body that has the mass square root 2 into m. So this body is tied with two strings, this and this one. Because the system is in equilibrium, so tension in this part of the string will be same but in opposite direction to the tension on this part. So that will be T1, but it will be acting in the opposite direction. Similarly, in this part of the string, there will be a tension T2, which is the tension that is acting here, but it will act in the opposite direction of this tension that is acting in this part of the string. The net component of these two tensions, because we can split it into two parts as they are acting at an angle with respect to this plane. So one component of this tension will be T1 cos theta 1, and the one component of this tension will be T2 cos theta that will act in this direction, that is perpendicular to the surface of this body. So we can write it like this because it's again in we know that this is the equilibrium system. So the addition of these two components, that is T1 cos theta 1 plus T2 cos theta, must be equal to the component of force or the force that is coming because of the mass and gravity, that is square root 2 m into g. Further, we know there will be another component of this tension along this surface, that will be T2 sine theta, and in this direction also there will be one component of this tension that will be T1 sine theta 1, and the body is not moving in this direction or this direction, that is left or right. So both of these forces must be equal to each other. So we can say T1 sine theta 1 is equal to T2 sine theta. Let's say these equations as equation 1, 2, and 3. From equation 1 and 3, this one and this one, we can say mg sine theta 1 is equal to mg sine theta. Or because mg will be cancelled out from both the sides, so we can say theta 1 is equal to theta. Both these angles must be equal for the equilibrium state. That thing we know after these equations. And further, because we have to find the value of theta, so if we use the value of this theta 1 is equal to theta, let's say this is the relation or equation 4, and 1, that is T1 is equal to mg and T2 is equal to mg. If we put these values from 1 and 4 in this relation that is defined as equation 2, then we can write this equation 2 again as mg cos theta plus mg cos theta is equal to square root 2 mg. Or because mg will be cancelled out from both the sides and this will be simply 2 cos theta. So we can write 2 cos theta is equal to square root 2. Or further we can write it as cos theta is equal to 1 by square root 2, which is nothing but the value of theta for 45 degree. So our answer is, for the equilibrium state of this system, the value of theta must be 45 degree. So this is the answer. Now we move to the next problem. Next problem is, what is the maximum value of force F such that the block shown in the arrangement doesn't move? So here, as shown in the problem, we are applying a force at an angle of 60 degree with respect to this plane. The mass of the body is square root 3 kilogram. It is resting on this surface. And here the coefficient of friction is 1 by 2 square root 3. So let's find out the solution of this problem. We can see that there are multiple forces acting on this body. One is the downward because of the weight or gravity, and one is acting upward perpendicular to this surface, that is the reaction force. And we are applying this force, so we can split it into two components. One is along the surface, that will be F cos 60 degree, because we are applying this force here at an angle of 60 degree. And one component of this force F, will be downward. This will be F sine 60 degree. We can say that on the upward direction, there is a one force N, and on the downward direction, we have two forces mg and F sine 60 degree. And there is a no movement in upward or downward direction. So for this equilibrium state, N must be equal to mg plus F sine 60 degree. Let's say this is our equation 1. And for body at rest, frictional force that is must be equal to F cos 60 degree. Because if we are applying a force in this direction, that is towards the right side, then there must be a force that will be because of the friction, that is a frictional force that will be acting on this direction towards the left side. And we know that after applying this force, the body is not moving, it is still at the rest. So the value of this force, component of this force, that is F cos 60, must be equal to the value of the frictional force. So we can say frictional force is equal to F cos 60 degree. Let's say this is our equation 2. Value of frictional force, we know we can calculate it using this relation, that is coefficient of friction times reaction force. Mu times reaction force value we can get from equation 1, that is mg plus F sine 60 degree. Now using the relation 3 and 1, using the relation 3 and 2, we can calculate mu mg plus F sine 60 is equal to F cos 60 degree. We can further write it in this form: F is equal to mu times m times g divided by cos 60 degree minus mu times sine 60 degree. This is just, we are just rearranging these parameters. We are taking F on one side and we are taking cos 60 and mu terms on the other side. Putting the values of mu, m, g and cos 60 and sine 60, we can write it in this form. This comes out to be 4.9 divided by 1 by 2 minus 1 by 4, and the final value of this force comes out to be 19.6 Newton. So this is the force, the value of force that we are applying here at this angle on this body, and under this force the body still remain at rest because there is a frictional force that is acting in the opposite direction. So our final answer here is 19.6 Newton. That is the value of the applied force. Now we move to the next problem. Our next problem is two particles of mass m each are tied at the end of a light string of length 2a. The whole system is kept on a frictionless horizontal surface with the string held tight so that each mass is at a distance a from the center P. Now the midpoint of the string is pulled vertically upwards with a small but constant force F. As a result, the particles move towards each other on the surface. What will be the value of acceleration when the separation between them is 2x? So let's first understand this problem. So the problem states that we have two particles m of mass m. One is here and another one is here. They are tied with a string, and here is the center of the string, that is say P, and the position of particles from the center is Q in both the sides. Now you pull the string from this center by applying a force F in the upward direction. After pulling in the upward direction, you reach to a state when the separation between the two particles or the two bodies along this horizontal direction become x from the center or 2x from each other. So when we reach to this final state, then we can see that there are multiple forces will be acting on this system. And for solving this problem, we have to know, or we have to identify the direction of these forces. So first, let's start with this point P, because on this point we are applying a force F in the onward direction, and this point P is actually the midpoint of these two strings, and in each of this part of the string there will be a tension T, and this is marked here also. This is the tension T in this string. Let's assume there is a plane here passing through this point P, and these strings make an angle theta on this direction, and this string makes on this direction with respect to this plane. So we can say that this tension T will have two components. One is T cos theta along this direction, that is, this is the horizontal direction, and T sin theta that will be in the vertical direction downward. So both these tensions, that is T in this string and T in this string, they will have two components in the downward direction. That will be T sin theta plus T sin theta, that will be the net downward force. And there is a one force only acting in the upward direction, F. And for the equilibrium state here, because this point P will be in the equilibrium, we can say F is equal to R. R is the net force that is acting in the downward direction. That will be equal to 2T sin theta. Let's say this is our equation 1. Now assume, suppose this particle as a system, and say what type of forces will be acting on this system. Then we can see, because this is the tension, this is the string at an angle with respect to theta from the horizontal plane. Then there will be one component of this tension, that is T sin theta, will be acting in vertical direction, and T cos theta will be acting along the horizontal direction. There is a one force that is acting in the downward direction on this body, that is mg, because of the weight. So here we can say T sin theta is equal to mg. This will be valid for both the bodies. And T cos theta will be equal to mass into acceleration. This component is coming, or this relation is coming, because when we are pulling this string from this point with this force F, then these two bodies, they are also moving along the horizontal plane towards each other, and we assume they are moving towards each other with the acceleration A. And to produce that acceleration, there must be a force acting on these bodies along this direction, and that is your T cos theta. So this T cos theta is equal to mass into acceleration. From relation 1 and 3, 1 is this and 3 is this, we can write ma is equal to F by 2 cot theta. Or we can write further it in form of F by 2m, that is A, or the acceleration is equal to F by 2m into cot theta. Here we see this angle with respect of the string with respect to this horizontal plane is theta, or this angle of the string with respect to theta, this angle or this angle, they will be same. So we know the value of this string, the length of this string here from this body to the center, that is already defined in the problem. This is Q. And after certain time, as defined in the problem, this distance from the center of the body to the center of the separation between the particles is x. Then we can calculate the value of cot theta. We know the value of this arm, we know the value of this arm, and from these q and x, we can find the value of cot theta, or we can write the cot theta in terms of these two values. That will be x upon square root of q square minus x square. So by using this value of cot theta, we can write our acceleration in this form. Again, here in this problem, the value of any, again here in this problem, the value of any of these parameters like f, 2m, fm, or x or q is not given. So we can write acceleration only in this form. We cannot find the exact numerical value of the acceleration here. So this will be our final answer. Our next problem is a block of mass 2 kg slides on an inclined plane, which makes an angle 30 degrees with the horizontal. The coefficient of kinetic friction between the block and the surface is square root 3 by square root 2. What force should be applied to the block so that it moves A down and B up without any acceleration? So first let's solve the case of moving it towards the downside. That is our part A. So for moving downward, this is our diagram. This is the inclined surface that's making an angle 30 degrees with the horizontal plane. And here is our body of mass m. If we identify the forces acting on this body that are acting in different directions, then this is the force acting in this direction because of the weight. There's a one force acting perpendicular to this surface. This is the reaction force. And we know that this angle will also be 30 degrees. We can get it from the trigonometry. This will also be 30 degrees. So this force mg can be divided into two components. One is in opposite direction of this reaction force, that will be mg cos 30 degrees, and one will be along this inclined surface, that will be mg sin theta. Suppose here we are applying one force F so that the body can move downward. If it is going to move downward, then there will be another force, that will be the frictional force, that will act in the upward direction, that is in direction opposite to the movement. So from the direction of all these forces, we can see that F plus mg sin 30 degrees, these are the two forces that are acting in the downward direction, must be equal to the frictional force. Okay, and frictional force, the value of frictional force, we know this is always equal to mu, that is the coefficient of kinetic friction, multiplied by reaction force. Here again, from this diagram and component of these acting forces, we know that reaction force will be equal to mg cos 30 degrees, this force. So let's say this is our 3, this is our equation 2, and this is our relation for equation 1. From these 2 and 3, we can write the frictional force like this, mu times mg cos 30 degrees. Say this is our equation 4. From 1, which is this one, and this 4, we can write force, this is the applied force, equal to mg times mu cos 30 degrees minus sin 30 degrees. Now putting the values of m, g, and mu that are already given, and value of g we know, this is 9.8. So putting these values in this relation, we can calculate F as 2 into 9.8 into square root 3 by square root 2 into cos 30 minus sin 30. And putting the values of sin 30 and cos 30 in this relation, we get the final value as 10.99 Newton. So this is the value of the force that we apply to this body so that it can move in downward direction. And this is our answer of this part of the problem. Now, second part of this problem is what will be the value of the force when we move it in the upward direction. So in this case, the direction of forces will change slightly. Other forces like reaction force due to gravity and weight, and the component of this force will remain same. Only the direction of frictional force will change because now we are moving the body in the upward direction. So frictional force will come in direction opposite to the direction of motion. So in this case, the applied force F will be equal to mg sine 30 degree, which is the component of this force along this plane in downward direction, plus frictional force F. And we know the value of frictional force, that is equal to mu mg cos 30. We know it from the previous problem of the part A. And we can write this in this form, mg sine 30 degree plus mu cos 30 degree. And now again, putting the value of m, g and mu, we can write it in this form, 2 into 9.8 in bracket 1 by 2 plus square root 3 by square root 2 multiplied by square root 3 by square root by 2. And this comes out to be, final value comes out to be 30.58 Newton. So this is the value of the force that we have to apply on this body so that it can move in the upward direction. So this is our final answer of this part of the problem. After this, let's move to another problem. Our next problem is, in the figure, the blocks A, B, and C have masses 3 kg, 4 kg, and 8 kg respectively. The coefficient of sliding friction between any two surfaces is 0.25. A is held at rest by a massless rigid rod fixed to the wall, while B and C are connected by a light flexible cord passing around a fixed frictionless pulley. Find the force F necessary to drag C along the horizontal surface to the left at a constant speed. Assume that the arrangement shown in the figure, that is B on C and A on B, is maintained throughout. So if we try to understand this problem from this figure that is given here, then we can see clearly that there are 3 bodies, A, B, and C. Their masses are given and they are stacked over each other. This body A that is on the top is fixed or hold here by a rigid rod which is connected to this wall here. B and C are tied with a string and this is going over a pulley. This is a frictionless or smooth pulley. And here we are applying a force F. Coefficient of sliding frictions between any two surfaces means between C and this bottom surface, between B and C surface, and between A and B surface are given. And this is 0.25 for all these cases or between any two surfaces. So we are applying here the force F in this direction, and we have to find the value of this force so that C can be dragged in this direction towards the left side at a constant speed. So we can see here, first we can write the values that are already given in the problem. Masses of all 3 bodies are given here. 3 kg, 4 kg, and 8 kg are the masses of body A, B, and C respectively. Coefficient of kinetic friction is 0.25 for any two surfaces. Further, we can see that the frictional forces that are acting between these different surfaces can be calculated using these relations, like the frictional force between A and B will be equal to mu times ma into g. Ma is the mass of this body that is on the top. Frictional force between B and C, that is between these two, will be FBC, which will be equal to mu times the mass of these two bodies, that is Ma plus Mb into g. And frictional force between C and the ground surface, that is here, will be FCS, which will be equal to mu times the total mass of all these three bodies, that is Ma plus Mb plus Mc times g. Let's say these are our relation 1, 2, and 3. Now we see, as defined in the problem, we are applying a force F on this body, that is C, and we are trying to drag it in the left direction. So to know the amount of this force, let's first identify all the forces acting on the B and the body C. So if we pull the C or drag the C in the left side, and the C is connected with the B with this string, so this string, there will be a tension in this string, and it will try to drag the B in right direction. So we can define it like this. This is the tension that is on the right direction, acting in the right direction on the body B. And there will be two frictional forces, FAB and FBC, because this body B is in contact with the body A, that is on the upper side, and body C, that is in the bottom side. So it is in contact with the two surfaces of body A and body B. And we can say this T will be equal to FAB plus FBC. Further, for this part, that is the lower body C, and here we are applying this force F in this direction. So correspondingly, the frictional forces, again here will be two frictional forces, because one because of the surface friction B and C, and one will be because of the friction between the C and the bottom surface, that is FCS. And this T is because of the string connected there, so tension in the string. So we can say here from this diagram that F will be equal to T plus FBC plus FCS. Say this is our relation 5, this is our relation 4. Putting the value of this T from relation 4 into this 5, we can rewrite it in this form. F is equal to FAB plus 2FBC plus FCS. Now putting the values of FAB, FBC, and FCS from our earlier relations of 1, 2, and 3, we can rewrite this value of capital F in terms of mu and the masses of the body, and G like this: mu times in bracket 4ma plus 3mb plus mc into G. So putting the values of the given values of all the masses and value of G, that is 9.8, and coefficient of sliding friction, that is 0.25. Here we can put all these values in this relation, that comes out to be like this. And after solving this simple relation, we will get F is equal to 78.4 Newton. So this is the value of the force that we have to apply here on this body C, so that it can move with a constant speed in this direction or towards the left direction. So this is our final answer.
Our next problem is an insect crawls up a hemispherical surface very slowly, as shown in the figure. The coefficient of friction between the insect and the surface is 1/3. If the line joining the center of the hemispherical surface to the insect makes an angle alpha with the vertical, what will be the maximum possible value of alpha? So let's first try to understand this problem with the figure as given in this problem. So here is the hemispherical surface, and there is a one insect as shown in the figure. It is trying to climb up. It's a crawling up. So at any given position or any instant of time, there will be multiple forces will be acting on this insect. We can see there will be a force normal to this surface. This is a reaction force. This is given by N here. This is acting in this direction that is perpendicular to this surface. And this is also along the line joining the insect with the center of this hemisphere. And it's making an angle alpha with this vertical line. There is a one force acting in the downward direction because of the mass and gravity. And there will be one component of this force that will act in this direction perpendicular to the surface but opposite to the reaction force, and this will make an angle alpha with respect to this force. And there will be another component of this force mg that will act in this direction, that is tangential to this surface. This will be mg sine alpha. When the insect, so now let's see, when the insect is crawling up, then at any instant it's not falling because two forces are acting in opposite directions. One is because of the weight or the gravity. This is acting in this direction. This is mg sine alpha, and the force, this is basically trying to pull it down. So because of this force, it can fall down. But at the same time, there is a one force. This is due to the friction. This will be acting on the opposite direction, and it will not let the insect fall down. So if it is not falling, it means frictional force is higher than this component of force that is acting in the downward direction. But there will be a certain condition or one condition when it is slowly moving up. So this mg sine alpha, the value of mg sine alpha will increase because you are increasing the value of alpha, while the f value of frictional force will be constant. So at some position, this mg sine alpha will be equal to f for a particular value of alpha. That will be the maximum value of alpha. Above that, if you go, then value of mg sine alpha will be higher comparing to the frictional force, and the insect will start falling down or coming down from its position. So we have to find out the situation when this value of f is equal to mg sine alpha, or we have to find the value of alpha at which frictional force and the downward force, that is mg sine alpha, are equal. So here we can see, now let's start writing the values of these forces. So we know the value of n, that is the reaction force n here, will be equal to mg cos alpha because there is no movement in this direction. So this is equilibrium state and these forces will be equal and opposite. So n is equal to mg cos alpha. Frictional force, we can write f, we can represent it by small f, and it will be equal to mu times reaction force. This is the standard relation. And as defined in the condition, for the maximum value of alpha, f will also be equal to mg sin alpha. So this is the maximum value of alpha up to which the insect can crawl up without falling down. So now from 1, 2, and 3, 1, 2, and 3, from these relations, we can simply write it in this form, that is mu mg cos alpha is equal to mg sin alpha. We are just putting these values in these relations. And from here, we can write mu is equal to tan alpha, or the value of mu is already given, that is 1 by 3. So we can write simply tan alpha is equal to 1 by 3. Or in other way, we can write it as a cot alpha is equal to 3. Now, depending on the the nature of a problem, suppose you are asked to provide the specific value of alpha, then you can further solve it and find the value of alpha that will give you the value cot alpha is equal to 3. Or if in the multiple choice or single choice type objective questions, if this is the answer in this form, cot alpha is equal to 3, then you can leave your answer up to here. So this is our final answer.
So this was the last problem of this session. With this, we end this session of solving the problems on laws of motion. It was my pleasure solving these problems for you. Thank you for your attention. Bye.